Hey, do you want to make me moderator so I can bring people up and post the link?
Sure, Katrina, no problem.
How are you today?
I'm
Everything
doing
good?
great. How are you?
Good, good. Thank you. Sorry that I'm late.
No problem.
I'm 6 minutes earlier.
Yeah, I can understand. It's the mid of the week.
Okay. Hi, everyone. Let me ping in some people. Is it okay if we wait 2 minutes, or I'll
Yeah, of course.
ping
Yeah,
in some
sure.
people? Okay, perfect.
I would do
Hi.
as well. Yeah.
Okay. Welcome, everyone. Hi, Kiko. Hi, Denise. Of course, special thanks to Rupesh that he's presenting today. Go ahead, then.
I just wanted to say hi, everybody. It's really fun to see Rupesh, who's been with us in the audience and on stage, but now he's a presenter. This is so cool.
Oh, thanks. Cause yeah, I because I did some research and I thought it would be a nice idea to present, and Katrina was really helpful, uh, during the process.
Yeah, congratulations to your PhD. It was in January, right? Your defense, as I saw.
Oh,
Or...
that's right. Yeah, it was last January.
Nice. So, yeah, I think we can slowly start and by introducing you, and we'll ask you the general question, and people will start coming in. It usually takes around 10 minutes, but that's fine. We chat and ask you a few general questions before you start your presentation. So let's start with that. So welcome, everyone, to the Science Society. We have our guest invited speaker that is also our member here, and as Denise said, he comes to the stage, asks questions. So it's an honor to have you here today. And let me give you an introduction. So, Dr. Rupesh Ghimire, is that right? How I'm saying it? I hope it's.
Yes, you almost got it right. It's
I'm sorry.
Ghimire, but it's no problem.
Ghimire. Okay,
Mhm.
Ghimire. He's a postdoctoral scholar at the University of California, San Diego. And he is a theoretical physicist, and his work involves numerical calculations and data analysis in simulated real-world areas. During his PhD, he gained experience in studying the effects of ultra-fast electromagnetic waves in two-dimensional materials. He theoretically proposed a nanolaser based on the properties of localized surface plasmons, whose peculiar properties can be used for several real-world applications such as cancer research and telecommunications. And for his postdoc currently, he's studying the effects of high energy photons, electrons in the treatment of malignant patients. And yeah, he did, as I said, he did his Bachelor of Science in Trikandra, and then he did his Master of Science in Physics at Georgia State University, and his PhD in condensed matter physics at Georgia State University. So, yeah, it's a great honor and pleasure to have you here. Denise, do you want to ask the general question first?
Absolutely, be my pleasure. So Rupesh, thanks for joining us as a presenter. It's very fun to have you come from audience to presenting. And the first question we like to ask is, what was your journey to professional science? When did you first realize that this is what you wanted to do? And you can answer the question as broadly or narrowly as you want. Sometimes people take the 5-minute route, the 10-minute route, whatever you would like to disclose to us, so that we can inspire future generations of scientists.
Well, thanks, Katrina and Denise. Yeah, so I was like most of the people will say the same thing, but I was also like I was kind of curious about how things would work, how things work. Like uh, I used to like open up electronics, like look at the things inside the circuits and everything, like when I was like 7, 8, and I always wanted to know like reason behind like how it works. Look, I read several magazines or like books and everything. But as I went on with my studies, I found that probably physics is the best answer that would reasonably satisfy me because you come across so many interesting things like okay why does this happen and this does not, right? And so I started like studying physics, and uh, so once I completed my uh, bachelor's degree, I joined a master's degree there, and then I came to US because there was a really limited opportunity in Nepal in terms of like how you want to go on with your research. And yeah, that's what. And since then, I'm like, I have finished my PhD, so I'm like more like in the same field at this time. Yeah, that's what my journey is. That's what I can tell.
Right on, thank you. That's a great answer. Katerina, do you have anything else?
No, thank you. That's a great answer. And yeah, please uh, go. The stage is yours for your presentation.
Oh, thanks. So yeah, I will now start my presentation, and so the topic is nanospaser. I'm like, I think this is kind of vague topic when you just read the letters there. But but in the next few like slides, which I have here, you can download the slide. I will also mention the page number. So in the next few slides, I will give the introduction of the field and what is nanospaser. It's slightly different field to what we have conversation in here. So let's start. And the outline is I will give an introduction to nanoplasmonics, which is a field of optics in itself, and then a spaser, which is a laser that works in the principle of nanoplasmonics. And since I have decided to like introduce both of these terms, so it will be relatively easier for you to grasp there. And then I will go on to the nanospaser, which is the topic for today, where I will discuss like theoretical details and the formalism conclusion. And so in the introduction, so what is nanoplasmonics? So we discuss optical phenomena like in terms of like photon or electron. Most popular is we look the electronic behavior in the band gap of the semiconductor and all those things. But here in nanoplasmonics, we deal with those type of optical phenomena in near the metal surfaces, and there is reason why it needs to be a metal surface. And as it has nano in front, you can assume that the dimension where this phenomena occur is really small. So the history behind it dates back to 4th century. It's a long time ago, and probably we just have like uh, some artifact that are left right now. And one of these artifact is Lycurgus cup. The cool thing about this cup is it when you look it from one direction, it shows one color, and when you look it from the other direction, that is from transmitted light, say, it will be seen as a different color, and that's the presence of some nanoparticle inside the cup, which change the behavior of the light transmitted. Uh, so uh, people were able to harness that property of nanoplasmonics like long time ago, like we can only imagine how long it was. And uh, so if you have a gold nanoparticle, let's say you have different shapes of gold nanoparticle. I'm looking at slide number 5. One of them is rod shaped, one of them is circular, and two are triangle. The dark field images that you get from these nanoparticle are of different colors. Uh, our pre-assumption is that okay, gold will appear like yellow, but probably not. If it's a nanoparticle, it can be of different color. Uh, and okay, these colors are cool, right? You have a wide range of spectrum that looks fancy, but what's the actual use of nanoplasmonics? Like, why do we use it? The reason it stems from is uh, how like how sort of the distance or how what limits you to confine the photon or the electric field modes inside an object. So right now, if you use a two-plane mirror and you try to obtain electric field mode inside it, right? So it should have minimum dimension of 100 like 500 nanometer, which is shown in like figure 6. That we are limited by the space between the mirror, and that will kind of limit our ability to fabricate devices which work on very small dimensions, let's say nanoscale, because world is all about miniaturization right now. So it is possible, like, okay, light, we can obtain electric field mode, very high intensity electric field in a nano object by making use of special type of boson, which is called surface plasmons or localized surface plasmons, which I will discuss later. And yeah, so what is a plasmon in the first place? So uh, when the uh, electron density inside an object, it vibrates in a metal, it vibrates like with a very high frequency. You will see it like all the electron, it kind of like, forms a pattern of oscillation, which is very high, and it is independent of any external thing, and it's a characteristic of itself, like of a certain metal. So you say plasma frequency of gold is this, plasma frequency of silver is this, and and we can't like really do anything about the plasma frequency because it's ranges into like higher than 8 electron volt. So next thing, we need a frequency or the mode of oscillation inside a metal which can exist in like in the visible range, most preferably because we want to fabricate devices from that. And second important thing is it should be tunable. So if you cannot tune the frequency, like what's is used, because you have to couple it with something, right? So we use surface plasmons and localized surface plasmon. Now, plasma frequency, yeah, plasmons are more like longitudinal waves, is like sound waves, whereas the surface plasmons are transverse waves. In slide 8, I have shown you, I have like put a figure of how the charge density inside a metal are separated. Like when you polarize when you shine a light, the charge density is separate and they oscillate in the presence of these restoring force rays, which are always there. And since the charge density, it varies in a smaller scale, like much smaller scale, like nanoscale. So the electric field which is there uh, uh, can be used to confine light within that nano regime instead of micrometer now. And so what is surface plasmon? So you have so let's say you shine a light, which is in X and G direction with a p-polarized light. You have magnetic field in another direction. Then solving the boundary condition between the metal and dielectric interface, you will see a condition where there will exist waves along the surface of the metal. Now, let's say that these two mediums, like we don't know if it's metal yet, but the condition on which the wave sustains, it's such that the the object where the wave sustains should have a negative dielectric constant. That is why metal is the suitable choice on that. Now, these waves or these oscillations are kind of lossy because these are limited by like very high relaxation, and uh, and the uh, let's say it decays in G direction. If it travels in X direction, which is given by Kx, where Kx is spatial wavelength or wave vector, inverse of the wavelength, yeah. And this Kg is given by the frequency of light, something K naught is associated with the frequency of light, and also the direction it travels. So the
Rupesh, just quickly
yeah.
to clarify. So,
Mhm.
from what direction axis the light, say the E field, in
Or
what direction is the light,
it's in the
the E
XG
field light?
plane. It's in the XG plane. Uh, so it's a p-polarized light. It's an XG plane. Magnetic field is just in the opposite side,
So,
uh, perpendicular
if
to
I'm
it.
imagining light as
Mm-hmm.
has a
Mm-hmm.
it's a torch, so
Mm-hmm.
the light propagates in X direction.
Oh yeah, the light comes from the one plane, and the waves propagate in the X direction. The surface plasmon wave, which generates in the surface of the metal, it travels in the X direction. The field, it decays in the G direction.
Right.
It's like the yeah.
So far, my difficulty is that I understand the plasma wave propagate in direction X,
That's
and
right.
it decays in the direction Z. I'm asking
Exactly.
in
Hmm.
what direction the light is being shine upon this system. So from which direction, and from that direction, I can.
Hmm.
There's also the degree of freedom of polarization, right? So.
Oh, it shines from the what do you call it, from the top direction. So it's within a plane light. So one component of the light vanishes. So how do you say it?
So it's the Y
It's
direction,
it's the y direction in this case. Yeah,
and it's a
it's the y direction, but it has ex and ey. So if you have an incident light, yeah, it has EX component and EG component present there. So it's a plane light.
So
So
it has both component
mhm.
EX and
Right.
EZ.
Yeah, that's right.
Okay, it's not polarized.
Mm-hmm. It's a plane.
Rupesh, this is probably a figure in the presentation. Is that right?
Oh yeah, just the introductory figure. This is yeah.
Slides 8.
Slide 8.
Yeah, the left figure. Yeah, thank you.
Please continue.
Okay. So what we have is like in the wave vector, which is the surface plasmon wave travels, that is kx. Now is much longer, like much say has a greater value because it is now associated with the dielectric which is present outside, and now it can be modified. So you have shorter wavelength, because if the wave vector is longer, you'll have shorter wavelength for the same frequency. And let's say the wave vector is kind of like infinite. That's where we define the plasma frequency is. Another type of plasmon is localized surface plasmon. So we see the same behavior here. You have light that separates the electron density into positive and negative charges on two sides. They oscillate in the presence. Of the restoring force, which which uh, uh, has certain frequency, and this frequency is uh, totally dependent on uh, two factors. So one is the shape and size of the object. Like in nanoparticle, we saw different color. It so it's because like what shape of the particle that is, you can change the frequency of resonance. So in this localized surface plasmon, this is the characteristic of this nanoparticle. The decay function of the plasmonic field, or how fast the field decays in the metal sphere, or whatever the shape that is inversely proportional to the dielectric permittivity of that metal in that given frequency. In slide 10, there is this representation of how the field will look inside the surface plasmon. So these are evanescent field traveling along x direction. In LSP, localized surface plasmon, you have separation of dipole. Uh, so you have a dipole field. You can also have a quadrupole field, but dipole field is much more stronger. So you have fields on two sides there. And let's study the feature of the nanoscopic system. Like, okay, I said there is a confinement within very small volume, and we can define it in terms of quality factor, which is how like how many oscillations a electron like does within the given relaxation time. It's not that high as in case of electronic system. It's like 10 to 100, but what compensates is the number of electron that is available. It's very high in terms of in the nanoscopic system. Also, the volume is small. So all these characteristics, what you see here, it gives a ideal scenario of a laser system, because you can make a really robust laser if this field can be confined with, like, considerable quality factor, and you have all these characteristics there. And applications are wide ranging. So you can have it as a indicator, because there is always a resonance thing in there. So whenever there is a resonance, you can tune into that resonance and see the hotspot, like in the diagnosis, imaging, sensor, all these things. Also, you can have like what do you call it? You can make it as a switch, like, because the resonance are mostly like delta function, and it can also work in detection of ligands and so many other different things. So yeah, so detection of ligand is one of the applications. The application which I'm going to focus here is the spaser. So you have a nano laser, which is small, like 30 nanometer wide or even lesser, but it's inside a living cell, which can range from 1 to 100 micron probably. So uh, you can imagine the possibility is immense in this, because uh, this source of uh, laser or source of light inside a cell can be tuned in such a way that it can kill the cancer cell, or it can, diagnose some disease and all these things. So let's talk about spaser. So what is a spaser? Spaser is like, it stands for, I'm in slide number 14. It stands for surface plasmon amplification by stimulated emission of radiation. So you will amplify surface plasmon here uh, instead of photon, and the theory is the same. You'll have the same stimulated emission. So it's the counterpart of a laser in much smaller size. Let's see the laser, like it's just a refresher, like how the laser will look like. You have a pumping source, you incident a light on the gain, you have an electric field mode within the laser cavity. So once you pump the population from ground state to, say, excited state, it will have some fast relaxation, get into the meta-stable state, and there will be spontaneous emission, and then there will be a stimulated emission, which will give a coherent beam of light, photons. That's our normal laser. It's the foundation of what we are today. Everything is based on laser. Another is spaser. Now, how is it related to the laser? In slide number 16, you will see that I have created, I have like illustrated a cell, nanocell, which is a metal cell in the presence of dielectric. Now it can support plasmonic mode, as the laser cavity will support the lasing modes, right? And the source of gain is the quantum dots that are present outside. What we'll do is we will shine light on on the quantum dot, which is the gain here, that will go into electron hole pair, and which will relax to the exciton. Now, the exciton, instead of going right now, it's not a plasmon yet. The exciton, instead of going through a radiative decay, which is like just like emit photon and go to the lower state, now, if it has a frequency comparable uh, to the plasmonic system outside, it will send its energy to the plasmon, which is present in the dielectric core outside. So exciton will pass the energy to the LSP. And now this will create a high plasmonic field, which will in turn excite more of the quantum dot into electron hole pair. And now you will see a laser-like phenomena in a nanoscale. So this is how spaser works. For our system, uh, what we do is we'll select a different geometry. We are trying to harness the topological properties of the spaser. So we have a metal system, slide number 17, which can support plasmonic mode, and the electric field mode is given by the Legendre polynomial. And let's concentrate to the dipole mode. One second, we also have a gain. So we named it topological spaser, which is a nanospaser. Now, how do we introduce topological property there? Is by introducing topology in the gain. These materials like TMDC are known for their topological properties because of the presence of valleys. So they have this K and K prime valley, which have the same energy or the transition frequency, just opposite. And the Berry connection is, which is, how do you say, it's analogous to the magnetic field, or the flux through the valleys is just opposite of each other. So we can say if the Berry curvature of one K valley is 1, the other will be -1. So there is a topology in the gain of the TMDC. How do we combine these two systems together to form a laser, which we call a nanolaser? Let's study that. Now, to do that, let's first see how the field will be inside the nanospheroid, which is the metal part. So field, if I take a vertical cross section, field is mostly centered around the two extreme ends, and on the other side I have the dipole, because every time we see the light matter interaction, or if we want to couple something, we see the field that couples to the dipole of the other any other material. So we have a field distribution in a spheroid and a longitudinal field distribution, I'll say, and we have a dipole of MOS2. This is dipole in one valley. In another valley, it will just be different. The field distribution in that was vertical cross section. This is horizontal cross section. The field will rotate with time, because since it's a dipole field, it will rotate in time. Also, the dipole will rotate with time as well. So this is some theoretical details to see like how we can like compare those two compare the plasma frequency of the metal to the frequency of the transition of the gain. So for that, we will have a parameter which is proportional to the experimental frequency, and we will get the same.
Sorry, Rupesh,
Yeah.
which slides are you on now?
I'm in slide number 20.
Okay, gotcha. Thank you.
Yeah, it's a theoretical detail, but I'm just trying to give you like a simple insight on that. So I have a parameter which is S. One depends on the experimental quantity, which is omega. So you find that as experimentally, and similarly you can find the value of that Sn by using the geometrical problem, by using boundary condition and all this. Now, once you compare those two, you will be able to obtain the frequency of the surface plasmon, say omega sp, by changing the geometry of the cell. So you basically, as I explained before, but this is in the theoretical way how we do that. We can change the shape and size of the spheroid. Say we can change the radius of the spheroid or height of the spheroid to change its surface plasma frequency. It is easily said, but to do this, we have to use this formalism. Also, the loss factor are also associated with this, which is given by those expressions. Remove the equation aside, and let's see here. So you have a spherical cell, you have a TMDC, you have a transition frequency of omega 21, you have a frequency of rotation of omega S, surface plasma frequency, or LSP, omega SP, in slide number 21. How do you make them equal? Is, in my case, omega 21 was 1.66 electron volt. So what I had to do was set the radius of this spheroid to 12 nanometer and the height of the spheroid to 1.2 nanometer, and that would do the math to equate these two parameters. Yeah, obviously this will rotate in time as well. So the flow chart is given there, where you have a incident light, any circularly polarized light. If it incidents on the TMDC, like to the material which have inversion, which breaks the inversion symmetry, you will have a valley polarization. So one of the valley will be populated, the other valley won't be populated. It was first demonstrated by Heinz in 2012, I guess. It was a really famous paper. And then once you have the valley polarization, what we'll do is, since this metallic cell where there are plasmons in close proximity to the TMDC, there's a direct coupling between the valley, which is excited, uh, and the electric field of the plasmon. So there is a coupling there. Now, this is called a direct coupling, but alongside there is also a chance of uh, excitation of the second valley of the TMDC by the field of the same mode, depending on what size of TMDC we choose. Because our intuition of our understanding of light of one polarity exciting the valley of one polarity is limited if we take a radius equals to 0. But right now we have a field that doesn't just like act on the center point of the TMDC. It's spreaded. So there's a chances that K prime value will also be excited, provided that TMDC is big enough. And once that happens, you will have both modes in generation. So we'll have the plasmons in one mode, and you will also have the plasmons in the other mode. That is, to say it simply, you will have a co-rotating plasmon in the system. You will also have a counter-rotating plasmon in the system. This depends on what size the TMDC is, or what frequency, what is the pump frequency of the light that you shine on the TMDC. And to study this light matter interaction, slide number 23, we describe it in terms of the Hamiltonian. So Hamiltonian is widely used in quantum mechanics to see the energy of the system, to study the interaction. So here we can separate Hamiltonian into three parts. One is gain, the Hamiltonian of the quantum dot, which is its gain, slide number 23. And then you have the Hamiltonian of the nanosystem, S bar omega sp. M defines the dipole modes, plus and minus one. And there's the interaction Hamiltonian. For the gain, we decided to interpret the system in the density matrix approach. So you have a density in the conduction band, you have a density of electron in the valence band, and you have two densities, which is the coherent population that are slowly varying with the time. It is more of a generalized approach because there can be another approach which does not account for this coherent population, and we can simply take the diagonal term. But this is more of a complete approach. The what do you call it? The Hamiltonian of the plasmonic system, though it's a quantum mechanical term because you have a creation and annihilation operator of plasmon, here we'll adopt a classical approach. Unlike the Hamiltonian of the gain, we adopted some quantum mechanical approach. Here we are applying a classical approach, saying that okay, this creation operator it's a slowly varying quantity, like you have a magnitude and it slowly varies with the time. So the number of plasmon that is generated in a system now can be given by the square of the amplitude of AM. That's the number of plasmon that is generated in the system. And M defines the indices. So M say it can be co-rotating plasmon or counter-rotating plasmon. Next is the interaction Hamiltonian. So you have gain, you have plasmon, and you have the interaction between the plasmon and the gain, which is in slide number 25, you will see the interaction between the electric field and the dipole. And it is sum over both the values, sum over all the area, because we have to take all of them into account. Now, it gives us to a simple idea of how to solve this equation is how the population changes in the gain, say conduction band and valence band of the gain should be equal to like the commutation with the Hamiltonian. So these are very common equation in physics. Uh, any evolution that you want to find, you should commute with the Hamiltonian, and that's what we have in slide number 26. So we have two equations as you see. One is the change in the population of the gain, another change in the population of the plasmon. What you will notice here is the change in the population of the gain is also proportional to the radius, like where it is located. Since the plasmon is formed in overall system, we take it, we do not really associate with like, okay, this plasmon is formed at this part of TMDC, this plasmon is formed at this part. However, for the inversion of the gain, since we are talking about the valleys, we have to say that okay, which area or which section of the gain has a inversion there or the population change. So that's why there is an R factor, which kind of complicates our problem. G here is the pumping frequency of the excitation light. And this will result in a very complicated equation, but once you solve it, you will get the number of plasmon in the system, you will get the change in the inversion, and so many different things. So let's go on to the results in slide number 29. And this figure here, which is the coupling amplitude between the electric field and the dipole. Uh, uh, so we are looking at different field. So m equals to 1 and m equals to -1, since it's a dipole field, with the same value. So with one particular dipole. What you'll see is if the coupling is, so in the center of the valley or in the center of the TMDC, the coupling is as expected, which is if you have m equals to 1, valley equals to 1, you'll have all the coupling center within the footprint of the nanodisk. So only the center area is where has a hotspot. However, as I said, there's a possibility of the mode that which are outside that can also be excited. That's what. So for large enough TMDC, which is greater than the size of 12, as you see in figure B, it will also have a hotspot there if the size of the TMDC is bigger. Now, this is the result in number 30, because that was all the explanation, like what process goes in there. You will have number NM, like figure A, slide number 13. Slide number 30, I'm sorry. You'll have a classic laser curve. This is a CW profile, continuous wave profile, where you have a pumping frequency on one side and the number, which is the intensity, on the other side. It is very common graph in all the laser and everything. So what you'll see here is, as you increase the pumping and it crosses a certain threshold, there is a generation of plasmons. In the case of light, there will be a generation of photon, but we were able to get these curves for TMDC size of 12 nanometer, a single curve plasmon in just one mode for a given frequency. So, and we use different TMDC as well, because TMDC can be MOS2, MOST2, and the only difference between these TMDC is their band gap, which and also the band structure, which changes its transition dipole. And that's why we have this curve. They don't coincide in the same line, but they are different because their dipole is different. In next, what will happen if you change the TMDC of different size? So for 12 nanometer, you only saw presence of one plasmon, that is one type of plasmon, m equals to 1. But for 16 nanometer, Well, you'll see two plasmons now, two type of co-rotating and counter-rotating plasmons. This is strange because the light that was incident on the TMDC was only in one direction, that was say co-rotating. But now the plasmons that you have here exist in both these are of both these types, co-rotating and counter-rotating, and over to it they have a different threshold. Well, that's that makes it even more complicated, but interesting in a certain way. For 18, you have two types of plasmon present, co-rotating, counter-rotating, but they have the same threshold. So figure A is a circularly polarized light, B is elliptically, C is elliptically polarized light. And in figure number D, we try to see like how the threshold changes with the radius. And we see that the threshold, it merges at 18 nanometer. To see like why this happens, we try to see the inversion, like how the the availability of this small population, it changes in the gain. And abruptly it came to the notice that how the inversion changes for 16 nanometer in case of there is a second transition step in the inversion is different to slide number 33, which is for 18 nanometer, which is just in one step. So it is more related to the inversion phenomena because now the TMDC is so large, it the uh, uh, outer atoms or outer chromophore in the TMDC is now excited by the other mode of light, other mode of plasmons. Now, let's look at the temporal dynamics. That is how it changes with time. So plasmon, uh, if you have same initial number of plasmon, say, okay, I supply the system with say a 9, 25, or 16 plasmon and see what will happen if I pump the whole system with 50 per picosecond. They all saturate to the same value. So the system is quite robust. It is, no matter what the initial plasmon population is, it doesn't really matter because all it sees is like what's the pumping frequency of light is present, and they all will saturate to one particular value. But however, if you change a different pump intensity, you will the number of plasmon will saturate to a different values. So that is in slide number 34. And these are slide number 35 with the temporal dynamics of the same phenomena of the classical continuous wave profile that I shown. So for 14 nanometer, you only have one mode. For 16 nanometer, you'll have two different lines given by solid and dotted line. And 18 nanometer, you'll also have two different lines, which is pretty consistent with what we have in the continuous wave. But now in temporal, it is also the same. The we also try to understand the far field radiation. Since there were, so we picked a case where there were two threshold, two modes. Okay, what happens? So we looked, let's just pump it by 50 picosecond, 49 picosecond. We saw a circularly polarized light, which only has one mode in the dipole radiation. When we checked, okay, what happens in the 70 picosecond, which is well past the threshold for both those modes, we saw an elliptically polarized light, and that's what the result is consistent about, like what we observed before. And this is the flow chart, like not the flow chart, it's the result chart, I would say, just a cover picture, where you sign one light, you get another type of light based on what size TMDC that you use. And these are the conclusions. The first conclusion is, the conclusions are all based on the radius of TMDC right now, because for a small radius, K and K prime values are mainly coupled to the co-rotating mode. For example, K value is coupled, coupled to the M1 mode. So there is already direct coupling there. For larger radius, there is also cross coupling between one mode and the other valley. And changing the pump strength, we can, okay, if we change the pump strength, we can change the handedness of the far field, because for a smaller value of pumping, there was field in one rotation. Like, however, for this higher value of pumping, we saw electrically polarized. So yeah, it also depends on the pump strength. And now, due to all these properties, topological nanospacer can be used for near field spectroscopy, because now it can take circularly polarized light as an input, and then you can get a desired light as an output. So it does work in spectroscopy, hopefully. And there is also sensing applications, since it's also related to the field. And these are some of the paper we published at the same with these results. And thank you so much. There's acknowledgement for my professor who passed away, uh, uh, and Dr. Mark I. Stockman and Dr. Apalka, who I'm still working with. And I'll also like to thank the funding agencies. Dr. Wu was a postdoc, and he was really helpful. Thank you.
Yeah, thank you so much for this amazing presentation. It's quite a lot of work that you did. It's very impressive. Congratulations again, and for those papers that you published during your PhD. So yeah, if anyone has questions, please flash your mic, or come up to the stage, raise your hand, and yeah, go ahead.
Okay, I'm not gonna pretend like I know everything that you said because I don't know a lot of physics, but I'm trying to understand. So, is it that these like nanoplasma plas I don't know how to say it. These like nanoplasmic plasma particles, maybe?
Nanoplasmonics,
Yeah,
nanoplasmonics.
yeah.
Yeah.
I'm sorry. Is it that they like their interaction with the light is like taking energy from the light so the wavelength gets longer? Is that like kind of like the like what's happening?
Yes, it's mostly you take the energy from the light, but what distance you need to concentrate the light field. So if you can have a photonic cavity, you can take the energy from the light, but you will still have to spend the considerable length there, uh, uh, in terms of hundreds of nanometer. But this one creates the same high field in the shorter distance. Uh, yeah, it is excited by the external light. That's why.
So is it like certain because like what really kind of got me like trying to pay attention, it was like the that in the beginning of your presentation you had like a jar that was like green on one side and red on the other. So it's to me saying that like you kind of discovered the method to how that's happening, but this is kind of like a natural phenomena. So like my question is this something that's like specifics to like solids, or can like a material behave like this in like a gaseous form? You know what I'm saying?
Okay, to give you an answer in short, it's related to metal nanoparticle. Nanoparticle are very small particle which you cannot see, but they behave in a way that is quite different to their bulk form. So you have a huge chunk of gold, it acts totally different to what a nanoparticle of the same gold will act, uh, because in terms of like how it vibrates, in terms of how it absorbs the light, right? That's why you see different color. And since that artifact which I showed in the beginning had a different had nanoparticle embedded inside it, they were observing light in a different pattern and had a resonance frequency that were different, so they gave different color. I hope that answers.
Yeah, yeah. Thank you.
No problem.
Rupesh, yeah. Also, I mean, congratulations. I mean, on the your research and PhD work is. I think you're lucky. I mean, you got such a deep dive. On the such an interesting, amazing, area of physics. So yeah, as well. I'm not. I'm, getting all the material you're trying to communicate, but just trying to learn and. Um, my question is I have a couple questions, but I'll just first try to understand your work better. So I mean, do you have a sort of a phase plots for the two controlling parameters, the gain and the size, so that and could you just repeat what? So there seems to be the merging of the threshold of G, and your but also as you increase the size, and so I get partially the picture of because what was the physics due to there's something going on with the exciting the coupling, right? So with the valley, that how strong, and seems as the uh, if the size gets larger, somehow the both uh, plus one and minus one, uh, well, that's the same it as well for G, right? So I'm not getting that part very clear. Could you go into a little bit
Yes,
more?
Frank, that's an excellent question. To be honest, like I wasn't really expecting about this question, but I'm really happy to answer. So what happens is, let's go to the slide where we had fields, and I can maybe hint you on that the flow chart. Let me see where that is. Yeah, it's in slide number 22. So if you follow that, you will see. So we all understand the direct coupling here between K value and one of the mode of the plasmon. Let's say you excite the K value, which excites m equals to 1 mode. That is what we all agree on, and that is pretty obvious. But the field in M1 mode, which is present there, does couple to K prime value of the TMDC. It seems like it does not,
So
but
the
since,
the
yeah,
the, the
mhm,
coupling, the
yeah,
physics of the coupling is due to the
mhm.
material. Yeah, so could you just a little bit more on the coupling?
Okay,
Is it off that diagonal
okay,
on makes it
right.
matrix?
Mhm. The coupling, though it looks unphysical because m equals to 1, coupling with the alternate value, but keep in mind that the one-to-one coupling is only limited to the center of the TMDC disk. So if you go like outward, which is very far away from the center, which is in the region like more than the footprint of the nano disk, uh, that's where two mode come. The the mode can couple to its the counter rotating mode, because we are not looking at r equals to 0 anymore. We are looking far away, and that's why the the size of TMDC, it does matter, in a sense that if it's sufficiently large enough size, you'll have enough number of gain chromophore, right? Gain chromophore in the region that is outside, and that can also produce the plasmons. Uh, so to say why they have different threshold and why some of them have same threshold, if if the TMDC is very large, then uh, then there will be enough number of gain chromophore there already there. So all the threshold that's in there, like they will come at the same time, uh, since the process comes simultaneously. However, if you only have limited number of gain chromophore, uh, but if you have like say 14 nanometer size, 12 nanometer being the size of TMDC, let's say 14 nanometer, 12 nanometer being the size of nanodisk. If you have say 14 nanometer TMDC, in that region, you won't have like affluent number of like large number of gain, but there are limited number of gain which are still excited by the K prime. But for that, for the generation of those gain, you still need to pump the valley, right? So it does depend on the pumping frequency now. I think I can explain you better than that, but Frank, do you get the idea or?
Yeah, I think I get a clue type of. I'll I'll follow up with that with
I'm
a
really
little bit
happy
more.
to contact you, and like explain this as much as I can.
Great. I mean,
Thanks,
appreciate it.
Frank.
I'll listen
That's
more.
a great question.
Yeah, thank you.
So thank you so much, Rupesh. That was wonderful work. And my question from you, specifically in a biological system, because I can see that you just talk about detection of the binding of ligands in a molecule. And in the same time, I can see the polarization inside the nucleus. And in another hand, you talk about the co-rotating versus counter-rotating. And my question from you, after applying all of those regimen to the molecule, or you call it a spacer or such a thing. So for the second one, do we still considering the same rules that you have, including the radius and excitation and the, I mean, pumping pressure and all of those things or not in a biological system?
Dr. Shah, yeah, thank you for the question. The thing is, in order to make things work to a certain frequency, uh, so if you sign say certain like certain frequency light and you want the system to be responsive, you have to match the frequency of that system to the incoming light. So that's the reason why we change the shape and size and so many things of that system. So yeah, that's a characteristic of the system. That's the way to tune its frequency. And oftentimes it's a fact that you can't achieve everything with the linearly polarized light. So you need to have a circularly polarized light, and and you need to have a system which accepts the circularly polarized light and amplifies it, because there can be some molecules which are responsive to the to those type of light. And yeah, this system can be useful for those.
So
But the
still you want to
what
say we have the
Mhm.
same domain, or we should introduce the spares in the same domain that you just introduced? For example, for the omega, you have a range, right?
Mhm.
So for spares, we have the same thing?
Yeah, the domain, it's right now it's in the visible to the near ultraviolet range, which is where most of the things work. But changing the shape and size, the domain can be adjusted. It's more about adjusting the frequency. So is that what you're asking?
Yes, I mean, most of my question, because everything is, I mean, makes sense for me. Instead of if we want to have another
Hmm.
spacer in the
Right.
same time after applying the first one. And why I'm asking, because for example, for some of the, I mean, approaching in a level of the DNA, which we have an expression inside the DNA, and we can just binding with the spacer. So I think that it does make a difference for whatever we have as a ligand in the surface versus whatever we have inside the cell. That's why I just try to get an understanding how these two kind of a spacer react to each other. Do we still have a co-rotation or counter-rotation and all of those, I mean, radius and all of those rules gonna work out for that or not? So Maybe
Um,
that's a new question.
so yeah, I kind of like understand if you want to put like two spacers at the same time, it's highly unlikely that they will react with each other because the distance between them is so large in terms of nanoplasmonics. It's a very localized system. So, but however, the characteristic of the spacer, which is the counter rotation, adjusting the frequency, all these things, they will still be valid for that system. So yeah, that's my though it's not experimentally tested, that's my assumption on that.
Thank you so much.
Thank you.
Rupesh, I guess a related question. So the 12 nanometer size, is that you design that based on some insight of after computation already, or you somehow from a previous literature you think that's the critical. And also the drawing seems the field itself, given the intensity gradient, seems that the reddish is still smaller, well contained in your. So there's some leeway that for your design. Is that a meaningful question? Hello.
Are you asking me, Frank?
No, I'm not.
Oh, sorry. I was muted. I'm sorry. So, first question is kind of obvious because we did wanted to match the frequency with the frequency of TMDC. So the only way is to change the size of the uh, spacer beforehand because we wanted to couple to the TMDC. So yeah, that was based. We did some calculation and said, okay, if you set it to 12 nanometer, you set the height to 1.2 nanometer, well, it will couple to the TMDC. First question.
Right.
And
This is
second,
this is the process when you mentioned the design to couple the exciton and to the what do you call it, plasma frequency,
that's right.
right? Okay.
Mhm.
Okay. So that's the
What
design
was your
process.
second question again? The second question is where I was
So
a
this
little bit lost.
so
Mhm.
right. So, I mean, sure you will. Without understanding the, my still the intensity scale of your picture that you show. There's a very red area that you show the M1 K. Then there's surrounded by a bluish uh, peripheral circle, right? So uh, uh, I'm first of all, so just to make sure I'm looking at the. So this plot is the axes are length, right? So it's a squarish x and y, both
That's
nanometers,
that's right. Mhm.
and but this is a frequency domain or what? Sorry,
This is not a frequency domain. This is a real space.
okay. So this corresponds to your looking down on your nano the
Uh,
spacer. Or?
yeah, this is the real space representation of TMDC, where you have a TMDC of like say right now we have say 15 nanometer or a little bit bigger radius, right? TMDC, you can see that, and the most of the coupling between the TMDC and that electric field in figure A, which is for one mode, and the one valley is centered around the within the 12 nanometer area. Uh, you said, why is there another blue line which is outside, and there is a yellowish line again, yellowish circle again? It's because uh, the red hotspot, which lies within the 12 nanometer, or which is in the center, is due to the coupling with the one mode. However, there is a cross coupling term uh, that uh, that causes the appearance of that glow in the outer area. That's the reason why. M equals to
Okay.
1. And yeah.
So if you get even larger, say, then you have the bluish circle. I mean, in the interior somehow.
Yeah, because with one mode, it will have a what do you call it? This bright red. With the other mode, you will have a purple circle because the coupling is essentially absent there. However, these rings on the outer areas, like in say 10 to 12 nanometer rings, which are outside those red or those blue areas, are due to the cross coupling.
Right, got it.
Thank you.
I have a question. So, in the end, you talk about the left and the right circularly polarized light and left elliptically polarized light. Um, does it? So, mm, maybe I'm outing that I'm not understanding it well enough. But does either one has a different application for visualizing different type of materials or proteins and so on? Like or are those or it doesn't does it matter like which way um the the circulation goes for imaging or it doesn't matter?
Um, I think it does matter. It depends on uh, the choice of materials that you want this nano spacer to kind of interact with. Uh, so mostly for materials which are kind of more susceptible to some certain handedness of light, it can be useful. If you want there to be a source of electrically polarized light by shining circularly polarized light, yeah, that can be helpful. Or it can also be used as a on and off switch, some sort of, okay, we are in this barrier, so let's cut off the elliptically polarized light. It's full circular, but based on, okay, this we have certain environment outside, so that will change the handedness of light. Uh, yeah, possibilities can be there, but we haven't like really thought it in terms of like the like its application on those area. We were mostly looking at, okay, you shine one circular polarized light, you get a different light that can be really good for some signal or some sort of thing. And at the same time, if you can if you can really interact with some molecule, that would also be might be useful. But that's still up for consideration.
And how fast would the switch be? Would it also work for different colors? Like you want to say, like you want to switch between, let's say, fluorescent proteins or some sort of fluorescence in a biological system. Would you be able to switch fast between the different right or left hand?
Theoretically, with some modification, probably yes, because we can change the dielectric environment, and that will create a shift in the frequency. And but I'm not really sure the range of fluorescence or like what range it goes there. Uh, Fluorescence, really haven't thought about it. Uh, I'm looking at like normal transitions. Uh, yeah, I still need to think more about on that front. But that's an excellent question. Thanks.
Yeah, I was thinking about FRET imaging, where you basically have two different fluorescent proteins, and if let's say some sort of ion like chloride comes, their fluorescent level changes, and then you calculate the ratio. But for FRET imaging, you would it would be ideal to some people, either you have two detectors, or I think it would be maybe more accurate to use this type of a left hand and right hand and distinguish it by that. But in order to have like a good detection, the switching would need to be relatively fast. But I'm not sure if it's even possible to image those proteins separately enough to calculate the ratio then.
Um, all I can say in this thing is this the process is really fast. Like it's in the range of electron volts, so everything is like the speed is not a question. Wouldn't be a question here. Uh, the thing is, plasmon they sustain uh, for time enough. They can get the input, and uh, other than that, it's really fast. Uh, yeah, but as I
Really?
said, yeah, yeah, go on.
Do you think this would work for tissue that's alive, for neural tissue that's
Oh,
alive?
yeah, the neural tissue is one very challenging thing because uh, the spaser, which in the previous form, which is a linear spaser, I would say, the sign light, it was tested on rats, and well, it was successful in diagnosing the cancer cell, even killing the cell. But always there is a chance that the energy that you supply through excitation is a little bit higher. It's like I think it's one order higher, or two, like two orders of magnitude higher than one order magnitude higher than the permissible limit. Yeah, so for the neural tissue, I'm not quite sure, but we did discuss about like what are the human implication of this thing, and since the guidelines are really strict, uh, yeah, it though if you work on lower frequency range, it can be probably useful by suitable choice of the gain and something. Yeah, as I said, haven't been tested yet. So
Yeah, I would. Yeah, for maybe in vivo, maybe it's too damaging, unless you have like a tumor in the brain. Maybe I don't know how good it will go through the skull, but I was thinking more for research purposes, and when you have cell cultures, or to look at basic science questions in neural tissue, it could be interesting to
yeah, that
see
would
like.
be challenging in that front. Yeah, in for tumor case, like you need high intensity beams and all this thing, but it's not that high either, like is in photon or like, because I've been working with these linear
Mhm.
accelerators, it's not that high for sure. It's a normal visible spectrum, uh, but let's see. I
Yeah,
think it
it's also
can be useful.
interesting to have something that's very fast, right? I think most of the time we have, and especially the switching, if you have a way to switch really fast. So how we switch between um, different types of excitation is most of the time you have then two different lasers, or and then you have to change the shutter, so the shutter is pretty slow, or you have to use excitation and then close the excitation part with a shutter to then do the imaging, and there's always a delay that is bad because some responses in the neural tissues really fast. So I think that's the interesting part
Yeah,
about.
I understand what you're saying, right? It's the switching, like it will be a same problem in this. The only edge this thing has over the other thing is it can really like be a source of field, or it can act as a micro source of very high intensity field. No, nano source of high intensity field. So, but that might not be possible for any other system, and might be used as a signature because, well, the light passes through one medium, probably that will change the frequency of the light. It still can see like how the laser is excited in that medium, and you can probably sense the system. So that's the, I'd say, very basic idea, but can tell more. Thanks.
Yeah, thank you so much, though. Yeah, does anyone have any questions? I see Abyss. Welcome, Abyss. How are you today? You want to ask a question? Come up to the stage, or anyone else?
Well, if I may, I mean, the so for the application side, the so your research essentially adding to the tool sets of already available the near field, all sorts of waves. So your research will enable for the chiral kind of a chirality characterization of the molecules. In vivo is hard, but in vitro is already doable, right? So, have you? What are the limitations? The roadblocks from your physics material research to device. Say the temperature. I haven't, seen you mention temperature. Seems to be a lesser, say the phonons and the environment and the thermal and dissipation is all not very challenging, right? So I'm just trying to understand the potential.
Okay, the system is kind of like robust to uh, several different things, like change in the environment because it's so localized, and it will only look at the environment which is in the right vicinity around it. But however, there is a temperature factor which we didn't account because we are looking TMDC there, and TMDC property does change with temperature quite a lot. So yeah, we also need to look at the distribution with respect the Fermi distribution and all those with respect to the temperature. Yeah, that's one of the hurdle, but uh, that might change the characteristic, but still, the it might still be viable uh, in that front.
Just
So
maintenance the issue. Abyss, I saw Abyss raise, but couldn't pull him up. Maybe some bug of the room.
yeah, I also tried. Okay, he's yeah.
Maybe
Yeah,
exit then come back and do you want Abyss? You want to try that?
yeah. I think it's a bug because I tried also earlier to pull up another person that raised their hands.
Yeah, I did accept his
Dakota.
invitation, but he is still not here.
Yeah, Dakota. I also tried to bring you up, but it doesn't
Me
work.
too. Yeah. Seems
Oh,
it's
Dakota
buggy.
now works. Hi, Dakota. How
Check,
are
check,
you?
1, 2. I'm doing well. Yourself? How is everyone? Hello, world.
Wonderful. Thank you.
Hello.
Glad that glitch is over with. Thanks for having me. Thank you for presenting, Rupesh. I joined a little late, but if I understand right, you're using kind of the principle of LiDAR, if I'm understanding right, at the nanoscopic level, using light to excite a emission of a particle that you're then measuring. And using visible light specifically Have you looked into submillimeter and terahertz imaging with um, detectors made from metamaterials, such as graphene and boron nitride?
Not really, because yeah, the first part what you said is it's sort of right because we're looking at the emission of the light from the spaser, but it is it should be in the visible region, and it, it's uh, the thing is the signature of this light due to the presence of like number of plasmons, the intensity of light is it can be easily detectable compared to like what you have as like a low intensity light. So uh, I am not sure like how to answer your question on that, but probably we haven't really tried or tested on those fronts.
Thank you. That answers it. Thanks. Yeah.
Thank you.
Hi, Abyss. It worked. How are you today?
Hi, Kat. Hi, everyone. Yeah, I've been having technical difficulties. Yeah, great work. I'm actually trying to catch up on like the presentation, but it seems very interesting. And I guess like this is sort of like a cursory question. I don't know if this is um, sort of touched upon your presentation, and I apologize for if it's been repeated or if it's out of scope. But I was going to base off of what Frank was saying, that there are some biomedical imaging techniques that actually operate on thermal confinement. So I was wondering if you actually also consider that to be sort of like a contrasting agent when you're mapping out, those small part of like cellular like organelles or small molecules in the in living tissue.
Yes, thanks, Abyss. So yeah, that's one of the prospect like we can probably look into that direction as well. But previously, the thing that is holding us from like higher temperature at this time is because we have used TMDC. In case of spherical geometry, where they use dye is a gain of the of the source of the radiation, that could fit in any environment. But now, since we are using TMDC, it has to be modulated, or the band characteristics will be modulated for that thermal environment as well. That's that's what I think.
Gotcha. Thank you.
Yeah, it's also interesting to see. It would be also interesting to see if you could monitor with this right versus left proteins and the switching of that. That would be another very interesting application because it's really not easy to monitor, but I know that with mm, I think with the system you could because it's also so fast. So that would be another interesting application. And the other thing is, I think you mentioned in the presentation for devices. Do you think this could be also a good way to monitor things like what's going on in the blood with sensors on the watch or something to get more information about the current, let's say, glucose levels and other information like that, maybe?
Yeah, those all those things they come down to the same thing, that is how the spacer will interact with the molecule, or like how can we integrate the spacer, like right now it's a source of radiation, it's a source of uh, uh, it's some system which amplifies the light or and changes the handedness of light. However, with the introduction of say proteins, which can be stimulated by certain helicity or certain rotation, or placing it in a blood medium, or like a chips or something. It's it's a whole different like biology is kind of, I would say it's kind of hard, since the setup is a little bit difficult to place inside a living cell, but in a more like in a controlled environment, it can be very beneficial. I think so.
Oh, do you know what? Do you guys remember we had the quantum battery charging, Frank? Um, where they said you would need a pretty strong laser for quantum battery to charge quantum batteries fast. Wouldn't this be like the perfect laser for it, since it's amplifying basically the and it's quite, focused and quite strong laser. So wouldn't this be ideal for quantum battery charging?
Oh, I mean, yeah, I mean so this is actually a very exciting thoughts, because on this platform, Karina, I mean, kudos to you. I mean, you have brought so many, such a diverse, all scientists from all fields, presenting here. I mean, in the same time, the vibes, some vibrations in the podcast to the entire world. So yeah, so what will, how powerful it will be if all the researchers start get interacting with each other. That's just amazing. But just you got me to think about this very exciting possibility. For the on that talk, I remember what they're proposing is the to me, I didn't attend your recap room, so I missed my version of takeaway from that talk is the author was able to no, the author proposed the way of charging like a qubit, like coherent qubit systems that are in a way that very similar to quantum computing, that it can have a kind of a quantum dominant power, right? So, say speed, comparing to a classical way of charging. Yeah, so that's essentially it's a quantum and also powered by laser. So if I think it's combined with this research. I mean, I don't know the range of the power. How do they compare? But yeah, with powering with these what do you call the spacer type of laser, I think it's definitely very interesting. Since the other one is very low temperature, uh, yeah, I think probably it's it's a possibility and very interesting. Oh, by the
Yeah,
way, how
and also I
for
guess like
Rupesh, when you say spacer, are we thinking about exactly the same like a laser that they're very coherent and very low spread in?
Yes, they are. The spreading is even more lower than that of the normal laser. The bandwidth is very sharp because it is uh, very much frequency dependent. So it has very sharp peak.
That's perfect. I wish, were you here, Rupesh? No, maybe, but Abyss was flashing, so please go.
yeah, I mean I was gonna say that that's actually a good idea. I was gonna mirror what Frank was saying, but I don't think they have weeded out the technical difficulties of um, you know, actually deploying, or at least like implementing that sort of charger. I guess like they wanted to show some kind of proof of concept, or at least like from theoretical perspective, that it is possible to charge um, batteries at a much faster rate than the traditional ones by employing the um, the quantum coherence and decoherence approach. So yeah, I guess like presenting this idea to them would be a very interesting one. But yeah, but my impression from at least what I gathered from that brief discussion I had with them was that they are kind of focusing on the theoretical aspect of it for the most part.
Yeah, yeah. The practical one was oh, is Eli up or oh, there you are. I don't know, Eli, if you were here for the quantum battery charging. So the practical work was partially done by another team, and they built upon, and yeah, it was theoretical work. So you basically um, um, mm, by the n, basically you get the n factor of um, a faster charging. So if you have like 10 the battery consists of 10 sub I don't know what the name is right now.
Qubits, effectively.
Yeah, then you are 10 times faster than a regular battery, and if it's like 7,000, what would probably be needed for Tesla, at least that's what was in the presentation. I think it was 7,200 or so. Then it's by the factor of 7,200. So instead of charging for 10 hours, they said you could charge for like 2 minutes or something. And it's
But the key thing is using one charger, right? Because right now we can just do like 7,000 smaller cells and 7,000 charging circuits,
yeah.
and go 7,000 times as fast.
And that's why I'm saying, and they said you would need a laser, a very strong one, and a very precise one. That's why I said Rupert's laser is perfect, maybe for that. I'm not sure, Eli, if you would agree, because I'm not an expert. But I think they were very open to come back, anyways. So yeah, we could arrange for like a combined meeting, maybe.
That's in fact really interesting. I would like to read about their research. What that is like seems like it's like manipulation of qubits, but like what those qubits are, what system those qubits are in, and what scale do they work? If because plasmonic system, the benefit is it it is a small source, has very localized the what do you call it, the output. So yeah, but I don't know much about their talk. Unfortunately, I missed it because I was really busy. I will like to. I would be happy to like read about it. Probably I'll search it in the internet. Maybe I can find it.
Oh, I'll send you the paper and the presentation. That's not a problem.
So that's great. Thanks.
Next time, come to the rooms, no, I'll send it to you. Let me. So, if anyone else also wants to know what we are talking about, I'll share the link also in the chat for their presentation and for their paper. Since it wasn't open access, I have it on my drive. So.
Yeah, I think Katrina, maybe one of these days in the future we can have a roundtable type of bumping ideas from the previous speakers on stage and presenters, and have them. I mean, yeah, I mean, so far the talks has been mostly in physics, neuroscience, and both communities are looking forward to talking to each other for application and the theory, right? So, and the tools. I think that would be beneficial for all, and also for the audience as well. So that would be very interesting. As you were looking, so I'm just adding this thought.
Yeah, I agree also. yeah, I was planning to do that maybe after the summer to invite people back, speakers back in a team, so that have overlapping interests and that they don't know from each other always. For example, we taught the physics room we had this week, right? They didn't know about Enrico Rinaldi's work, and the guest speaker we had from Hong Kong, uh, was it Dr. Chen, about
Chen, Dr.
yeah,
Chen.
about the gravitational waves. So that would be, for example, interesting to invite this team back combined with them. And we have different topics where we now have, and then Detlef Weigel, for example, was here, and he said he was so sorry that he missed a talk a few days before from his colleague, so he wished he was there. So I'll probably invite them as a team then together. And yeah, so I think we have different, and we heard from some speakers interest in doing that in the future. So yeah, we should definitely plan that better and go through all the, yeah, we have so many guest speakers also coming up. So yeah, we should do that. And Rupesh well, it won't be now, but maybe after, maybe in the fall, um, because we have booked rooms until the 20th of June or 23rd, if I'm not mistaken, and then it's kind of the summer. People won't be around too much, so we can plan for after the summer for sessions like this, I think. And to also not annoy people with our, with, with our sessions. So, that we don't annoy the guest speakers to come back and back. So, yeah, I think it would be really interesting.
I think myself as a member and not as a guest, so I'm like down to come here anytime. Like it's a pleasure like to hear people talk, and it's really exciting sometimes to hear what they have here.
Yeah, and today we heard your talk. That's amazing. It was really great.
Rupesh, I have more questions. If okay, so the well, first of all, what's your plan? Are you moving on to getting a faculty? And also in your research, in your PhD research, how long does it take you? I mean, during your work, the what takes more time, like the preparation of the materials? Do you have to do the lab yourself, or the theory computation?
It's mostly the theory and computation because the first of all is the idea. Uh, Once you know the spaser has really sharp emission spectra, you need to harness like some properties, so you will combine them with like certain type of material which can possibly create a new phenomena. But along with that, the challenges are you need to express as a theoretical, you need to express them in terms of code. And for my calculation, I think I had to divide that TMDC into some 1500 segments and calculate the field in each of them using code. So a lot of coding in there, and all of them should be put into one differential equation because the evolution of plasmon is in with respect to the time. So you have say 1500 equation in one time. So this is just being technical in terms of coding, but besides that, uh, yeah, because the lab part I haven't really touched it. My professor, like he, my advisor was there. He used to get involved in experimental research as well. Like, so he also really helped me on all these setting up these ideas. But he would just give a hint like, okay, how about you try this, and we would try to make a system that would support the case.
I see. So, in terms of coding, it seems that this is all you have to do all that start from C or what do you Python or something, and any available like software like quantum, what do you call quantum chemistry type of DFT or some other
Oh no,
any of
I didn't use limericks or DFT. Those, though it's one of also one of the available tools in there. I just use some Mathematica, MATLAB, and Python. But uh, we try to express the field equation in terms of the theoretically given mode, like we said it as a Legendre polynomial. So it's not like you have to simulate the structure there. However, the expression of the field, we calculated all the field value, and then we had to multiply with we had to see the interaction with the dipole. So it's not like DFT or numerics, but yes, fair amount of calculation, I would say.
Yeah, I mean, very interesting. I mean, this. So yeah, I guess you probably already move on to postdocs, and this is I'm looking forward to in terms of application and theory wise probably it's also, I mean, this is topological materials is it's in very red hot right now, so maybe some new quasi particles that you will try. It's very interesting. Yeah, thank you. And I'll Abyss, um, Mike is yours.
Thank, yeah, thanks, Frank. So Rupesh, I have a question for you. Hope I'm more audible now. Switch different system. So you said that biological systems are very difficult to deal with, and I agree with that. Have you experimented with different kinds of plasmon resonance energies that you can actually pick up from your system? Because I think even though like for metaparticles and nanoparticles, mostly you can actually find the plasmon resonance, whether it's bulk or whether it's surface, you can actually do that from, like at least from theoretical estimation, and you can go down from there. But I'm just wondering if that's possible for biological systems, and what you have observed if you've done any work in that area.
Uh, uh, I think there was a part I mentioned, like in 2018, there is a paper. It's called Spaser is a biological probe, where they did this experiment in mouse. So they literally injected that spacer, which is very like nanoscale thing, nanoparticle inside the mouse, and uh, uh, coated with a dye. So when they shine the light, it was able to identify the cancerous cell. So it's not like it cannot be used. It's just like really hard to tune in sometimes, since the requirement of biological the what do you call it, the health requirement is very high, so hard for human trials and all this.
Gotcha. So you're saying that you need some kind of contrasting agent, whether that's a nanoparticle, whether it's endogenous or exogenous. Is that correct?
Yeah, that's correct.
Got it. Thank you.
Yeah, do you have more questions, anyone? Um, if not, I would like to thank you so much, Rupesh, for coming and presenting, and this was such a great presentation, and the images, all the figures were really really good. So I appreciate you taking the time to explain this to us better, so we can understand your work. And thank you everyone for coming to the Science Society. We will have more rooms to this week, since we have more people from Europe, we will have them at an earlier hour. So tomorrow we have a room at 1 p.m. EST, and Dr. Alaham talking about Parkinson's disease specific gene signatures. And on Friday, we will have at 2 p.m. EST Dr. Sarwat from IBM in Switzerland, and he will talk about two of his papers. One is pretty recent, and the other one, he just published another one that he told me today about neuromorphic computing neural networks. That will be really interesting. And then next week we'll have again more guest speakers. We will have Dr. Spontek talking about improving efficacy of CO2 capture, and Dr. Finger how he could transplant pancreatic islets to cure diabetes. That will be really exciting. And artificial photosynthesis systems for CO2 capture will be on Friday. And then we'll have another physics room with Dr. Shoshani. He summarized from a conference different presentations about faster than light travel and time travel. He's a theoretical physicist, and he's summarizing his work and also from a few of his colleagues, and presented to us. So thank you so much for coming, and a special thanks to our special guest speaker today, Rupesh, Dr. Rupesh. And yeah, have a good evening or morning or wherever you are. Thank you.
Bye,
Thank
everyone.
you.
Thanks, Catherine.
Thanks,
Thank you all
everyone.
for being
Bye.
here. Thanks. Bye.
I'm so sorry. I didn't close the room. I pressed the wrong button. So
I'll do it.
bye. Bye. Oh God. Bye.